Welcome back. Today, we will continue our discussion on the antibacterial or antifungal, antiviral, those type of agents which are classified as antimicrobial agents, okay, or antimicrobial drugs. We have seen that penicillins, the one of the first antibiotic that was discovered. Before that, there were antibacterial agents that were available. One was salvarsan, which was discovered by Paul Ehrlich, and then Sir U. N. Brahmachari discovered the ureastibamine, and then followed by Paul Domack. He discovered the sulfonamides, the Prontosil, as that, which is the name of the drug. But these are all antibacterial agents, they are not produced by any microorganisms. So, then came the era of microorganism derived antibacterial agents, which are called antibiotics. Okay, and the first one to be discovered was penicillin, and I told you the history of the discovery of penicillin. And we ended up by saying how the penicillins kill the bacteria, and the one line answer is that it stops the biosynthesis of the cell wall that is essential for the bacterial survival. And the cell wall was composed of a peptidoglycan, where the peptide chains are hanging from the glycan units and the peptide chains are cross linked. It is basically very similar to what is called vulcanization of rubber, that you can make the soft rubber into a hard rubber by cross linking with sulfur, with disulfide, trisulfide kind of bonds. Okay. So, it is very similar that if you have peptide chains hanging, you can make the cross links amongst the peptide, and then that makes the cell wall very rigid and which can hold the cytosol, that means all the ingredients in the cell intact, and does not allow a free passage of molecules from outside. Only when it is required, those type of molecules can enter. Okay. Now, the later stage, the last stage of the cell wall biosynthesis was the is called a transpeptidation reaction, and the enzyme is called a transpeptidase. And what it does? It actually catalyzes the transpeptidation reaction, where a glycine amine attacks a terminal D-alanine peptide and replacing or removing one D-alanine, the terminal D-alanine, and that is replaced by the glycine. That is in gram positive bacteria. In gram negative bacteria, that glycine, the lysine arm where the glycine is present, that is replaced by diamino pimelic acid, the mesoform. Okay. But the mechanism remains the same or very similar. Okay. Now, why penicillin blocks the cell wall biosynthesis? The reason is that the penicillin structure resembles the structure of the dipeptide, that is the D-alanine. Okay. So, which part is resembling? This is the part that if you look at the structure of D-alanine, that is written on the right hand side. So, you have CO2H here and up to that point, and then you have this. So, this is the part which is present in D-alanine peptide. Okay. The stereochemistry is also similar, CO2H and CO2H. And because this beta lactam is very reactive and it resembles the D-alanine dipeptide. So, what happens? The CO2H is basically present as CO2 minus. So, there is in the active site pocket there is a serine and there is a positively charged handle in the presence of a lysine ammonium ion, and here it is the serine. So, the serine attacks the beta lactam and breaks the beta lactam. Okay, that. So, and then it stays there for a long time. Only after a long time water can come and attack this acyl enzyme complex and release the enzyme, but by that time the cell is lysed, that means all the contents of the cell are released. It could not withstand the internal osmotic pressure for a long time. Okay. So, the cell wall has to be synthesized very quickly, it cannot wait for the enzyme to be released. So, this is your transpeptidase enzyme. Now, what happened soon after the discovery of penicillin, there was one scientist known as his name was E. P. Abraham. Okay. E. P. Abraham, and E. P. Abraham, he was the one who suggested the beta-lactam structure of penicillin. That is the first thing that what he did. Then he observed that there are some microorganisms which produce an enzyme which can hydrolyze the penicillin and release itself from the penicillin. That means, it is another enzyme which is very similar to the transpeptidase enzyme, but the difference is that it goes and attacks and then is released by water. So, what I am saying that as soon as penicillin is attacked by the enzyme, in case of transpeptidase, this remain intact for a long time, but in case of the enzyme that Sir Abraham detected was that it is immediately hydrolyzed and you get a hydrolyzed penicillin, and the enzyme is free, and this enzyme then goes and attacks another penicillin molecule and then hydrolyzes it. Now, remember, this hydrolyzed penicillin does not have any activity, this one. The hydrolyzed penicillin lacks the antibacterial activity because it lacks the beta-lactam ring, that is the pharmacophore of the system. So, this enzyme Abraham called as penicillinase, just from the fact that it hydrolyzes the penicillin. Okay. Later on, it turned out to be a very important discovery. So, that is number one, he established, he proposed the structure of beta-lactam, which was confirmed by Dorothy Hodgkins, and then penicillinase enzyme. Just right in 1945, when penicillin was introduced, first it is given to the soldiers of the Second World War who are infected with wounds and then infection, subsequent infection. But in the same year 45, Abraham saw the danger, that means there are enzymes which can destroy penicillin, and he called it as penicillinase. And then he searched for whether other microbial products are there which can withstand the penicillinase activity, because what happens, the bacteria which produces penicillinase enzyme, they are inactive, they are basically resistant to the penicillin, because the penicillin is made inactive by hydrolysis. Okay. So, then E. P. Abraham discovered another set of antibiotics, and these are called cephalosporins. Okay. Cephalosporins. Now, before the discovery of penicillin or right after the discovery of cephalosporin, see, from discovery going into the market takes a long time. So, what happened? Meanwhile, whatever penicillins were being used, they became resistant, they were not working to kill the bacteria. Okay. The first penicillin I told you was penicillin G, that is benzyl penicillin, and then penicillin V, that was a phenyl methyloxypenicillin. Okay, that is penicillin V, but these were not working against the microorganisms, because the microorganisms have started to produce the penicillinase. Okay. Then, so in meanwhile, people tried to make new penicillins. Now, how can you make new penicillins? Is by varying this group R, because penicillin, all the different penicillins that we have today, starting from this penicillin G, penicillin V, then ampicillin, amoxicillin, cloxacillin, methicillin, there are many penicillins are there, but their pharmacophore, that means the this part remained the same. Only difference is that because the penicillins are actually acylated, this NH2 is acylated to COR. So, you can vary the R groups, different R groups, and then it was found that if you make say sterically crowded R groups, sterically bulky R, then what happens? Then the water, it can resist the water from approaching the acyl enzyme complex. If that be the case, that means the penicillinase cannot work very efficiently, and that what you wanted. Okay. However, the trouble is that if you make the R group very big, then the enzyme transpeptidase also cannot attack the penicillin, because it is so bulky. So, you have to have some optimum size of R group. Then people tried to make different aromatic rings with different donor acceptor. All these different penicillins were made. Again, I reiterate that all depends on the variation in the R group. Okay. And this is very easy to make, because if you have this amine, which is by the way called 6-aminopenicillinic acid, which there is a big pharmaceutical company called Beecham pharmaceutical company. They are very famous for their antibacterial research, and usually the penicillin that we get, that we used to get in the 50s, were the penicillin G or penicillin V. Okay. And that means you already have the COCH2PH, which is the penicillin G. So, from there to replace, to hydrolyze back to the amine will be very difficult. Means what I am saying, that if you isolate the penicillin G, that means from the fermentation medium what you are getting is this NH, then CO, then CH2PH, benzyl, that is the penicillin G. But in order to make new penicillins, what you need to do? You need to hydrolyze this amide bond, make the free amine, and then acylate it again with different acylating agents. Okay. But that is very difficult, because if this is the more reactive part as compared to the acyclic amide bond. Okay. So, that will never be successful, that if you want to chemically hydrolyze this is the one which will be hydrolyzed faster. However, they could find some enzyme which can deacylate this bond. Okay. And ultimately, by several trial methods, Beecham came out with a system where the microorganism produces the free amine. The free amine, the microorganism, the end product is the 6-aminopenicillinic acid. By the way, this is 1, 2, 3, 4, 5, 6, 7. So, 6-aminopenicillinic acid is a crucial discovery by Beecham, because once this is available in gram quantities, kilogram quantities, so you can acylate by any acylating agent, RCOCl. So, all the pharmaceutical companies, even academic laboratories, they started to make whatever acylating agent they have, okay, and then started to measure the antibacterial activity, okay, and that is how ultimately different penicillins were made. Now, again coming back to the structure of penicillin, what is the requirement? Means what is the requirement of or what type of changes you can make in the penicillin molecule, so that it retains the activity without jeopardizing the activity. First of all, your lactam is essential. This is called structure activity relationship. That means you slowly take off certain structures, certain groups, and see whether the molecule loses the activity or not. If it loses the activity, that means that is essential. If it does not lose the activity, so you can strip off some of the extraneous groups. Okay. So, what happened if you remove the beta lactam, it loses the activity. So, lactam is essential. Then it was that bicyclic system is essential. All the penicillins are bicyclic, but I will tell you that today there are compounds which have a beta lactam, but they are not bicyclic. Some monobactams are also now available. So, that hypothesis that bicyclic is a mandatory, that is no longer true, but a majority of beta-lactam antibiotics are belonging to the bicyclic framework. Okay. So, but when it was initially, it was thought that only the bicyclic will work, but I will give you one example where a monocyclic beta-lactam is also now being used as an antibacterial agent. Okay. Then the stereochemistry, these stereochemistry have to be cis. If this is trans, the penicillin loses its activity. This stereochemistry is also very important. If you take the beta carboxy, it loses the activity, and the free carboxylate is also essential. You cannot remove the carboxylate, and obviously you know the reason, because I told you the active site is basically a serine and a positively charged arm, and this is the one where this CO2 minus will bind and bring the molecule towards the serine. Okay. So, that is why CO2 minus is very important. Now, the question is, so the variability is where you can vary the groups are, one is R, as I told you, other is these methyls. If you change the methyls, nobody knew that what will happen if you change the methyls, or if you change the sulfur, if you put oxygen, if you put carbon, whether that will retain the activity or not, or if you can make a bigger bicyclic compound like a beta-lactam and a 6-membered ring. So, all these possibilities were there. Okay. So, people started looking at it. Fortunately, always mother nature helps us in showing their pathway. Like I told you that cephalosporins were discovered by E.P. Abraham. Now, what are cephalosporin? It is a very similar compound with a beta-lactam here, with a sulfur here. It is a 6-membered compound, and then you have X here, you have a double bond here, you have a CO2H here, and you have the very similar acyl group. Now, here this will be a 7 position, like 1, 2, 3, 4, 5, 6, 7, and this is 8. So, the starting point for this compound to make different varieties of R is what is called 7-ACA, 7-aminocephalosporanic acid. Okay. Earlier it was 6-APA, 6-aminopenicillinic acid. This is 7-aminocephalosporanic acid, okay, 7-ACA. But in cephalosporin, you have little bit more option, like you can change this X also. You can vary the X, you can vary the R. So, there are 2 handles where you can change very easily. Now, coming back to penicillin, I said what will happen if you remove the methyls or put certain different groups, whether it has been tried. The problem was that this molecule was made by the microorganism. If you want to synthesize this molecule chemically, in fact, it was chemically synthesized by John Sheehan. Okay. I think the spelling it could be right, but I am not very sure. Sheehan, maybe one H is missing. John Sheehan at MIT, he synthesized penicillin, the first total synthesis of penicillin, and but the problem is the yield is it's a laborious process, long steps. Sheehan synthesis was to confirm the structure of penicillin basically, like many of the syntheses are. So, that will never be tried in the company to make penicillin. So, it is really very difficult to replace these methyls and see what happens to the biological activity. It is very difficult to change the stereochemistry here, because these are all generated by the microorganism, and microorganism makes only chiral compound in one form only, it does not make the other form. Okay. So, to make the other form is very difficult, you have to do synthesis. So, people see this one is little bit easier, you can epimerize the hydrogen because it is adjacent to a carbonyl, and then possibly with base you can epimerize this hydrogen. So, those type of studies are easier, and changing R is also easier, but changing the methyls are very difficult. But I will tell you today that how the entire penicillin molecule has been changed, and and in the process lot of new molecules have been discovered. Okay. So, let us come back to this cephalosporin. Look at the structure, it is now a 4-membered ring and a 6-membered ring. Okay. Now, the 6-membered ring, what is this, has a double bond here. Okay. In penicillin you do not have a double bond. Okay. Now, you know that the steric, the strain on the beta-lactam ring, if you can increase the strain on the beta-lactam ring, that will increase the reactivity of this carbonyl. Okay. Now, how to increase the reactivity of the carbonyl? Why people were saying that bicyclic framework was essential? Because when you put another ring on the top of a 4-membered ring, then that increases the strain in the 4-membered ring. Okay. And this can be easily detected by taking the IR frequency, the carbonyl stretching frequency. So, that has been done. So, it was found that penicillin carbonyl stretching frequency is very high. That means, whatever little conjugation was going on, that is just cut off by putting this 5-membered ring. Now, if you have a larger ring here, a 6-membered ring, so what will happen? The reactivity of the carbonyl will go down. Now, so what nature has done? So, nature knows that a 5-4 combination is very good, you do not need any double bond or anything, and this carbonyl is very reactive. But when you have a 4-6 system like in cephalosporin, so what you have? You have to now activate the carbonyl little bit more, because this is a 6-membered ring that cannot impose the same kind of steric strain what the 5-membered ring can do. So, nature has put a double bond here. Why? Because now the nitrogen lone pair, instead of going to that side, can conjugate on this side. If it conjugates on this side, that creates a positively charged nitrogen, and if it creates a positively charged nitrogen, that activates the carbonyl, because the more positive charge on this nitrogen, the more reactive will be the carbonyl. You can think it another terms by the by thinking of the leaving group character of the nitrogen. That is also possible. That is also you can say. You can also say that this nitrogen, when it leaves, creates an N minus which is delocalized. That also you can say that the leaving group character of the nitrogen, amide nitrogen, whereas the beta-lactam nitrogen is more if you have a double bond here. Now, to prove this hypothesis, people have saturated this molecule, that means removed the double bond, and then found that the activity drastically reduced. So, the double bond is very essential. Okay. Now, the interesting twist to this happened when here there are 2 penicillin molecules very well known. This is ampicillin and this is amoxicillin. Only difference is that you have a hydroxy here, but you do not have the hydroxy. That means, the hydrophilicity people are modulating, and that actually initially amoxicillin and ampicillin in the 60s and 70s were very good. They could kill many of the microorganisms, but now they are rarely used alone, seldom they can kill the bacteria. Now, what happened? I told you that if it is a 4-5 system, you do not need any double bond or anything, because the 5-membered produces enough strain on the 4-membered ring. If it is a 6-membered ring, you put a double bond here. Okay. Famous organic chemist of the last century, R. B. Woodward. He was trying to analyze these things. Okay. And what he proposed at that time, that suppose we know that a 5-membered ring is sufficient to activate the beta-lactam ring, so that it can show the biological effect, and for a 6-membered ring you need a double bond, that so that the nitrogen lone pair is pushed on the right side, conjugated with the double bond. Okay. So, he said that if we combine these 2 hypotheses, then we should be able to make a compound which is 5-membered and also containing a double bond. So, if you look at this skeleton now, it has got a 5-membered ring like penicillin, and it has got the double bond like cephalosporin. So, this was a remarkable compound that Woodward synthesized and showed that it is extremely potent antibiotic. However, one point you have to be very careful, if you make it too reactive, then what will happen, as you first of all, whether you can take it through the orally or not, through the oral route or not, because of whatever the stability of this type of molecules. If it is very unstable, then you run the risk of breaking the hydrolyzing the molecule just simply by water. But anyway, Woodward make many molecules, and I think these are approved as an antibiotic, a very good antibiotic. It was possibly the company Merck, they synthesized, took the Woodward's molecules, Woodward simply made these molecules by combining the two, cephalosporin structure and the penicillin structure, and his idea was that this will be better than penicillin, this will be better than cephalosporin. In fact, they are extremely good antibiotics. Okay. Synthesis is very, if you are interested in synthesis, I can just tell you that retrosynthesis is like this. How Woodward could make the double bond here? Not very difficult. Of course, means now everything looks simple, but when during Woodward's days it was not that easy, but he is considered the father of organic synthesis. So, you do an intramolecular Wittig reaction, and that will give you the this is what is called PNIM. I will also tell you about some of the nomenclature system. See, when you have a beta-lactam attached to a sulfur, this is the skeleton, that is called PNAM. If you have a double bond now, that is called PNIM, because you have a double bond now. Similarly, if you have, suppose you do not have the sulfur, but if it is replaced by oxygen, so this will be oxapenam. Okay. Then it will be, if you have a double bond, oxapenim. So, that will be oxapenim. Okay. If the sulfur is replaced by a carbon, that will be called carbapenam. Okay. Carbapenam. And then if there is a double bond, that will be carbapenem. So, that is how the nomenclature system goes. If it is a 6-membered ring, then that will be like in the cephalosporin, biologically active cephalosporin, where there is a double bond, that will be called a cepheme nucleus, because you already have the double bond. If there is no double bond, then you have cepham. Then you can have oxacepham or oxacepheme, you can have carbacepham, all these are, that is the nomenclature system. Okay. So, this is a penim, because it has a penim skeleton. Penims are extremely potent antibiotics. Okay. Now, we have said that right from the word go, that means right from the introduction of penicillin, within 5 years, first of all, E.P. Abraham 1945 he published a paper where he showed that existence of penicillinase, where that is an enzyme which hydrolyzes the penicillin and make it ineffective. But then subsequent years in 1950, what happened? The hospital started reporting that penicillin is not working. So, hospital borne infections, you know that most of the infections, especially the resistant infections, they occur in the hospital, because in the hospital you have patients coming from different areas, from different poverty, different economic background. So, all these together, and also you apply the drug there. So, what happens that hospitals are the most dangerous place for staying for a long time. Yeah, it's not like a good hotel that you are saying there. So they actually harbor lot of these resistant organisms. So 1950, I think St. Mary's Hospital reported that the existence of these microorganisms where penicillin failed to act. Okay. So people started from that day onwards, people started looking. They know that penicillin is not the final answer. Okay. But I remember that when I talked to my father, who was there at that time, he told me that when penicillin, that news of discovery of penicillin came, so everybody thought that all bacterial infections now are gone because penicillin is there. But within 5 years that myth is busted. Okay. Now the question is how the bacteria acquire your resistance. Okay. So there are the many ways. I will talk about only the organic chemistry part by which the bacteria acquires the resistance, and that is the most important part. Achha, one way that bacteria can provide a kind of pump in their membrane where the molecule enters penicillin. See, I told you about the especially the gram negative bacteria. There is this lipid bilayer, then there is a space and there is a thin cell wall, and then another lipid bilayer. Okay. So if penicillin has to work, so it has to enter through the first barrier, that lipid bilayer. Okay. So if it enters, suppose if it enters, entering is a difficult thing, and if it enters, then there are basically like pumps that it will again pump it out from the system, that is called efflux pumps. So efflux pumps are one of the main reason for many drugs, many anti-cancer drugs which work initially, but then it cannot kill the cells, the cancer cells, because of these efflux pumps. This is a very common mechanism by which the molecule is thrown out of the cell if it tries to enter. Okay. So that is one. However, there are now this efflux pump means you need energy, because to run the pump you have to have an energy. So these are also called ATPase. The pump actually gets the energy by hydrolyzing the ATP. Okay. And then it operates these efflux pumps. Okay. Because you need energy. The other is that what it does, it can actually produce much more concentration of the cell wall, this transpeptidase enzyme, so that it can outnumber the penicillin. Means whatever penicillin you are giving, the bacteria produces more molecules of this transpeptidase, so that it can, some of the enzymes are inhibited by penicillin, but still there will be some enzymes which are left, so they can do the job. So that is the second option, but still you can bypass that by increasing the amount of penicillin. So that will continue. The bacteria produces more transpeptidase, you also increase the dose of penicillin. Interestingly, penicillin is very harmless because of the fact that it does not target any enzyme system which is required for the host. It only targets an enzyme system that is required only by bacteria. So I think that is, there is no such other example where a molecule only touches the bacterial machinery and does not touch the human machinery. That is why still today these beta-lactam antibiotics are the drugs of choice for any bacterial infection. Okay. Now after these two mechanisms, the third one is the interesting one. What it does, I told you about penicillinase. So bacteria started producing this another type of enzyme which are penicillinase, hydrolyzes penicillin, but because penicillin is very specific, it is the 4,5 system, but you can have carbapenems, you can have penems, you can have cephalosporins. So better call it, because it is hydrolyzing the beta-lactam. So this group of enzymes which hydrolyzes the penicillin are called beta-lactamase. Okay. So, this beta-lactam bacteria started producing these beta-lactamase enzymes, and in the next session we will tell you about the problem of beta-lactamase today and how to tackle this problem. That will be in the next session of this lecture. Thank you.